All right, good morning or good afternoon, I should say. All right, I'm going to record an introduction video. This is Unit 5, Transformations of Functions in our Algebra 2 class, but this could also be applicable for a pre-calculus class. I'm not 100% sure if within this class we're going to get to this unit. However, whether we get, if we don't get to it, then, students can view this for themselves. And if we do get to it, some students can use this for review or for just kind of, just reviewing up the skills if they missed it in class. All right, so I'm going to start talking. The word transformation means a change of or change in a function. And what's meant by that is something pretty specific, such as a function can be transformed by a translation. This is something typically you've encountered in geometry days, maybe in the middle school. We are possibly going to talk about reflections. I'm not 100% sure how much of this I'm going to get in this video, into one video, because to try to cram all this into one, that would be a pretty long video. I am going to talk about symmetry. I think that's kind of important. And let me see if there's anything else. The moving functions, that's translation, reflections. Yes, we are. Oh, okay. Yeah, we are going to talk about reflections as well. Okay. I'm just not sure about this stuff back here. So I'm probably not going to cover the whole unit in one lesson, in one video. But I'm going to do, an introduction to it at least. Okay, let's start. So the word transformation, as I mentioned, means change. But before we get to that, let's talk about, okay, let me move that. I don't know why that does that. Okay. So we're going to talk about the notation of functions. So as a basic notation of a function, I could call f of x, kind of like this, where the input is the variable x, the independent. And we typically call that letter y, but the function itself is called f of x. This is an f, because you can have a different function, let's say a g of x, and I could still call it by letter y, where the idea here is if I were to graph this, this would be like my x coordinate, whatever I put in here is my x coordinate, and this would be the output is the y coordinate. So this y and this y are really not referring to the same values or the same the results of same functions, because they are different functions. I am going to talk about I'm going to introduce this idea of inside the function and outside the function, and I'm going to do this both in a generic way and in a specific, with a particular example. So if I have a function, well, in fact, I'll call it f of x. That's the original function. Y equals that. So what's inside the function is what's being manipulated inside this parenthesis as a variable x. Whereas, so as an example, if I do something to the letter x, replace it by maybe x plus 4 or x minus 4, or if I replace x by something, it would look like this. X, let's say minus 4 on the inside. So I'm going to call this part inside the function. This is the inside part. So in this case, on the inside of the function, I replaced x by x minus 4. And we'll talk about the meaning of this. What exactly does that mean? What does it do to the function? On the other hand, if I say outside the function, what I mean by that is if I have y equals f of x, and I'm doing something to the outside of the function, I'm really doing something out here. So let's say plus 4 out here. Okay, this is what I mean by outside the function, whereas this on the inside of the function is this. So I'll give you a specific example over here, because this is generic, just a general f of x. So for instance, if I have a function y equals, just a basic, x to the third, like we'll even do x to the third. Okay, that's a parent function for a cubic. I didn't do anything to it yet. There's no transformation on this yet. This is a basic function, a parent function. Now, if I wanted to do something on the inside of it, I replace this. This is my function, right? Like something to the third power. And what goes inside here, what I'm replacing it with, is an example that x minus 4, sort of in parentheses. I'm going to rewrite this in a cleaner way, so x minus 4 cubed. And I'm going to call this, well, this is not going to call it, just going to refer to it as I transform the inside of the function, on the inside of the function, because the function itself is x to the third power. On the other hand, if I did something to the outside of the function, yes, I'm still creating a new function. I am still doing something, y equals, and in this case, the inner part, so this is y equals x to the third. So the inner part stays the same, x to the third, and if I do minus 4, this 4 outside of this quote-unquote parentheses, even though there's really no parentheses to look at, this is the outside of the function. Okay, so kind of be a little more complicated than this? Yeah, a little bit. So I'll give one more example to really solidify the inside and the outside of the function. So let's say my function is not a parent function, because this is already, I'm coming up with a new function. So something like y equals 2x squared plus 3x minus 5. This in itself is already a transformation, and we'll talk about how do I know that and what that is. This is already a transformation of the basic function y equals x squared. This is like the parent function, the basic quadratic. How do I know it's quadratic? Well, the highest power is 2. And then somebody came along and changed this, manipulated this to become this. Okay. But even this, I can manipulate to become something else. And in this case, if I were to say, well, let's replace x's by, so replace x into x, put in x plus 5 as an example. Well, this would be y equals 2. Now this is the inside of the function. X squared is part of the, it's the inside of the function. And here I'm going to plug in x plus 5. It's squared. And I'm going to continue plus 3. And again, this in here I'm going to plug in x plus 5. And notice, it's a power of 1, invisible 1 here, and then minus 5. That minus 5 doesn't get to be, manipulated. It's just negative 5. So there's no variable to follow. So this is a transformation. This is a transformation, and I haven't told you what kind of transformation. It is a change. Clearly, it's a change of this function, which in itself came originally from this. So we kind of started off with the parent function. We did something. Now I didn't really show you what I did here to get from here to here. Maybe the next slide will demonstrate that. I could continue from here to here, and theoretically I could open the parentheses here, simplify it, and come up with a different appearance of this function. And maybe I should demonstrate it. I don't know if it's worth it, but it's a short investment of time. If I were to manipulate by opening parentheses and simplify it, what is it going to look like? Well, y equals, let's actually do this pretty quick. This is going to be x squared, so 2x squared. Next one is going to be, this is 5, so it's 10, so it's 20 x. This is going to be 5, so it's 50 plus 50. So there, I just opened these parentheses right here, and at the same time multiplied it by 2. And hopefully you followed that. And to continue this is plus 3x plus 15, and then minus 5. And combining like terms to simplify it, well, my like terms are x squared is by itself, there's nothing else. So with this combines with this, and then the terms without letter x combined together. So all in all, at the end, this is y equals 2x squared plus 23. Oh, that was an ugly 23. X followed by 60. Looks like plus 60. So even though these two functions, well, first of all, these two functions don't look the same. However, they are the same function. It's just here I opened the parentheses and simplified it. But the point here was this. So I'll start off as 1 is what I would have started with. 2 is already a transformation of it. And these two functions, they look different, but they are a transformation of this one. So there's like, there's a bunch of transformations happen here. And the transformation, really, the way I did it, I replaced x by, on the inside of the function, by some x plus some value. In this case, it's a plus 5, but it could be something else. And we'll talk about the meaning of, well, what does this do to the function, this plus 5 or minus 5 or whatever I would have put in there. Okay. Okay, let me, that was not good. Okay. All right. So the point of this particular slide is to, to introduce or talk about notation, but more importantly about what's inside when I say what's inside the function versus what's outside the function. Okay. Let's go to the next slide. So, all right, let me see how I wanted to approach this. So transformations could be, you know what, I might as well start. On this one. So there's a couple of ways of introducing transformations. The first of all, transformation that we're going to do right now is translation, right? So in fact, I'll go back to the very first slide, and there are translations. Translation is moving things around. I think it's an unfortunate word, translate, because usually people think of translation from one language to another. But I guess here the idea is you're translating from one position to another position. So sometimes it's also called rigid. Rigid means you don't actually change the shape of the graph, you just move the shape, to a new location. Well, how is that accomplished? Well, so I'm going to do the demonstration using a particular, this is, hopefully you recognize what this is. This is y equals x squared, the basic parabola, the parent function of all quadratics. But I also could be doing this with generic or general, like just f of x, kind of like this. And it could be, f of x could be like other functions, x to the third power, whatever, sine, cosine, log. It could be other more difficult exotic functions. Okay, the idea here is, well, what's my center right now currently? When I say center, what's my vertex? Let me actually do a different color so it's more visible. Well, my vertex is 0, 0. That's sort of the most important thing about a parabola, where it's anchored. And then there's a bunch of things that, yes, you plug a value and you square it, and there's going to be, notice there's going to be two same height for two different inputs, and that's just the nature of whether I put in negative, well, I'll use 2 here. Whether I put positive 2 or negative 2 in here, I'm going to get the height 4. Okay. All right, let's let me undo those things. Okay. So the transformations. So how am I going to transform this function? Well, I'm basically moving the function, and the way to see how I'm moving, if I'm going to move horizontally, horizontal motion, in other words, to this side or to this side, I'm going to affect the inner part of the function. So inside the function any transformation done to the inside of the function will show itself as a horizontal motion side to side. So as an example, if I were to do this, if say I'm going to translate this function by 2 steps to the left. Well, to the left. Okay, so to the left over here. So by 2 steps, so 1, 2. So over here, I want to move my whole function over here. How would I do that? Well, the horizontal motion is the inside the function motion. So this function would be on the inside. It would be x gets replaced by. Now this is going to be throw you off possibly, but let's make sense why this is plus and not minus 2. You're basically saying my original variable, sorry, my original vertex was 0. What value of letter x would make the parenthesis equal to 0? Well, it's x must be, it's plus 2. You solve that, x equals -2. That is my new location of the x coordinate. And why the x? Well, it's on the inside of the function. And we'll talk in a second about the outside of the function. So my new location, I basically took this vertex and I moved it to the left, to the negative side by 2 steps. So, well, let's do a couple more. So what if I wanted to move it to the right by, let's say, 6 steps? What if I wanted to move this parabola over here? Okay, I'll do different color over here. And without changing the shape of it, without changing the orientation, I'm not changing anything about it. All I'm doing, in fact, I'll show you what I'm doing. I'm going to kind of do this. I'm moving strictly in a horizontal fashion. So this is my original parabola, and I'm going to move it by 6 steps. So every point on the graph, every single point got moved by 6 steps. Well, that means every single x got affected by that. So the way this parabola over here would look like y equals, on the inside of the function, instead of letter x, it would be x minus 6 squared. And again, make sense of it why it's minus 6, not a plus 6, is because I moved my parabola by 6 steps in a positive direction. In other words, x must be positive 6 in order to make this parenthesis, the vertex value of it, 0. That's a pretty good way of making sense of it. Now, a horrible way, and we unfortunately we do say it in class. It's like, oh, it looks opposite of what it is. From here, it looks like I moved it -6 steps, but in fact, I didn't move it into in the negative direction. I moved it in the positive direction. Okay, but we do say that, even though it's really not the best explanation, but we do say that in class. Okay. Anyway, so what exactly is this right here? Well, it's this. I took this parabola and moved it sideways by there. So there is my new parabola, or transformed function. Okay, let me clear things up a little bit. So I'm going to put it back. I'm going to erase all this. Now, so that's the inside of the function. Now, what about the outside of the function? So outside of function. If I change something about the outside of the function, in other words, like y equals x squared, that's my original function, and then I do something on the outside, like +1 or minus, or x squared minus 2 as an example, that would be a transform function. What I'm doing, this part right here, this outside of the function, is a vertical shift. Oh, by the way, right, I could have called, I sort of called it. This is horizontal, I'll just abbreviate it, shift, because you're literally shifting it. And very often in class or in general, I'm going to abbreviate this, HS, horizontal shift. Okay, so this way I don't have to write the whole word. Okay, these two, on the other hand, this right here is a vertical shift. In other words, you do you do something to this, and then you in order to get the y, you literally do +1 or -2. So what it does is, at the end, it does this. Either +1, that would be the, notice I didn't change anything about the shape of the function. Okay, there. Or definitely did not do side to side. And this would be a -2 down here. Basically, like kind of focus as to what's happening to the vertex, because none of the shape is changing. I'm not affecting I'm not transforming the shape itself. So I'm just changing the position. In this case, it's a vertical up and down. So we're going to talk about. I'm going to clear all this out, and let me see. Clear it out. Clear it out. Where? Okay. Oh, yeah. That also did this part, but let me put this back because I kind of foresaw that it's going to erase it. Okay, so in this case, I'm gonna create a new function. So if the original function was y equals x squared, and I'm going to create y equals x plus 2 in parentheses squared, and plus let's say plus 1. You know, I don't know. It really doesn't matter what the numbers are. So let's actually recognize. So what is this right here? This has vertical shift of +1, meaning I'm gonna bring it upward, and this right here is a horizontal shift of -2. Why -2? Well, you could think. Well, I mean, there's two ways of thinking about it. Really, what it wants to see inside is really this, kind of like this. Maybe I should have actually explain what that is. This is a horizontal shift by c, and if c happens to be a negative number, what's going to be inside here is going to appear as a plus. Okay. So in this case, what am I right here? What am I doing? Well, I'm shifting my vertex to my new vertex location will be -2, comma +1. So -2, so -2, comma +1. So that's my new location. And I'm just going to drag, I'm going to translate the parent function over here. And that's my new location. So this right here is a formula for that parabola, for this graph right here. That's the formula for it. Now notice I'm leaving this in a vertex form, because if I were to open up the parentheses, I would lose some information. That I would lose where my vertex is. It wouldn't be very obvious. I would actually have to complete the square to get back to this position. So it's much easier to see the transformations when it's written in this form. Okay, and let's just do one more demonstration. Like a quick demo. Oh, okay. Well, you know what? Let me actually complicate things a little bit. So the original function, so I'm going to clear everything out again. Command V, I'm going to put this back. Because that's the one I'm going to be, I'm leaving the parent function there just to see, well, that's what I started with. And I'm going to do this. I'm going to say y equals, and negative x, I don't know, -3 squared plus 2. Okay, let's think about what's happening here. Well, first of all, on the inside, I have a horizontal shift of +3. In other words, in this positive direction. But on the outside here, I have a +2, so that means it's a vertical shift of up by 2. Okay, that's easy enough to see. But I didn't really specifically did not describe what this is. What is this number out? The negative does for us. Well, technically speaking, a full-blown version of this would be much more complicated than what a parent function is. A parent function would be basically this. However, a fully transformed with all kinds of things you could do to it would look like this. Y equals some letter A, some number A, but A letter represents it. B x minus c squared plus d. Well, that looks pretty ugly, unless you realize what's what here. Well, D is a vertical shift. That's not a big deal. This C here, well, the inside's always more complicated than outside, and there's a meaning behind this. I don't want to jump to the conclusion right now. Actually, address a very complicated version of this. Notice in my examples that I had here, there was an invisible 1 in front. That made things a lot easier. We're not ready for this yet, but we are ready for. I think we are ready for this for A. Okay. So what does A do for us? Well, there's two things that go along with A. A could be a positive number or a negative number. The negative part of it, the negative, so in this case what I have here is negative, like invisible 1. Well, the negative, what it does, it reflects. It's everything that was positive becomes negative, and sorry, that was a bad explanation. It reflects about its vertex. So I'll demonstrate what that means. Okay, so where is the vertex? Well, we just said from the inside here, the horizontal shift is 3, vertical shift is 2, so the vertex is positive 3, comma 2. So I'm going to go there, positive 3, comma 2, it's right here. So my new location is right there. And if I did not have this minus here, if that was just invisible 1, well, it would be just straightforward this. It's a translation, 3 across in the positive x and 2 up in the positive y, 2 up. Okay, so that would be this part. However, in our case, what I kind of jumped into like the next level of it. I put a minus here. Well, what does that do for us? Well, what it does, it rotates everything around the vertex. Everything that was going up is now going down. And the way to see that in our case, in this case, would be, I'm going to simply rotate this. Let me see, where is it? I'm going to rotate this in a kind of like, I need that. So let me actually rotate it here like this, and this is what it would be. So this is already two types of transformations. One, I shifted it side to side or up and down, so this is a translation, but I also reflected it. I reflected it, in this case, about, well, that's what it's called, about its vertex. Everything that was above the vertex now is below the vertex, and so on, every single point. So that's what, like these two, even though this parabola or quadratic started off as a basic y equals x squared, but I translated side to side by changing on the inside of the function, and on the outside of the function, corresponding whether it's horizontal or vertical shift. But I also I also reflected it with that minus sign in front. Okay. We're going to also talk about what if that's not a 1? What if that's a different letter, a different number? So let me clear all this out and demonstrate that. So let me, let's clear it. Okay. So I still have this. I'm going to put this back. Actually, I probably will not need this anymore because just where I'm going with this. Okay. So again, I'm starting off with a basic y equals x squared, and which really the full the full version of this function could be written like this. I'm gonna leave the inside simplified on purpose because I really don't want to complicate. That's more like an advanced step here. If I write bx minus c, I don't want to do that right now. So I'll just leave it simplified, where b is just 1. So this is x minus c squared plus d. Okay, so the only one that in this case b is invisible 1. It really simplifies things for us. Okay, so here's an example. Y equals, let's say, 2 x minus 4 squared minus 3. Okay. So in this case, the first thing I'll look at, what are my transformations? Well, the side-to-side and up and down transformations are really, really easy to spot. It's basically what happens to my vertex. My vertex was sitting here at 0, 0, and the new vertex is the vertical shift is down by 3, so it's negative 3. So my vertex is, the y is negative 3. And in this case, the x went in the positive 4 direction to find its intercept, if you will. So this is 4 here. Okay, so that's my new vertex. Now, what about this part? What about this? Well, this is what's known as a vertical, not shift, but vertical stretch. So in other words, every single point, so I'm going to do this. First of all, I'm going to transform this, translate this. My new location is 4, 3, so it's 4, negative 3. So, I should have picked, let me put a different number here because I'm off the, I don't have the graph there. So let's put a 2 here. So this is a 2, and we'll make this a 2. Okay, so this is a minus 2. This is, so it's a vertical shift down, and so this way I'm still on the grid. So this is 4, so right there, because I don't have anything left. Anyway, so now what? Well, if this was an invisible 1, if this wasn't there, my translation would be this, and I'm done. But at this point, by multiplying this part by 2. It is on the outside of the function. What I'm doing is I'm taking every single point along here, every single one, and I am stretching it by a factor of 2. I'm stretching everything by a factor of 2, which is kind of hard to see initially. In fact, what I think I'll do is before I translate it, I'm going to stretch it first, and I think it'll be a lot easier to see. Although you can do it from here as well, but it's not as obvious because it just isn't as obvious. So I'm going to put it back. Eventually I'm going to put it here. But the idea here is by doing the vertical stretch on this parent function, every point, as an example, what used to be right here, now it's twice as high. The only one that does not get affected is the 0, because 0 times 0 is still 0. But every other point gets affected. So as an example, this point right here, which used to be 1 and 1 up, now it's 1 across, but 2 up. And I'm going to take this off here and because of the symmetry, and on the left side and right side will be the same thing, because the x is, the negative x is getting squared. What this is going to look like is a parabola. So I'm going to do a couple of more points, but I'm not going to do too many. Just it's a little bit of a hassle to. What it does, it's a much faster rising parabola. It is still, the general shape is it is a quadratic, because I didn't change the degree of it. It's still square. I changed something on the inside, on the outside, and this is a vertical stretch. So again, you could kind of visualize as if you take every single point and you just stretch it by this factor. And the bigger this number is, as an example, y equals, if it was like 10 x squared, blah blah blah, it would be a very steep parabola, very just super like narrow parabola. The bigger this number, the steeper it goes up, the quicker it goes up. Therefore, it looks narrower. On the other hand, what if this number was a fraction? If it was a negative number, it would flip. It would flip down what we saw in the previous example. So I'm not too worried about the negative number, the negative coefficient in front. But what if this was like y equals 1/4 x squared, you know, whatever this is. Well, we'll just leave it at this. In other words, here, what's the translation from side to side? None. Right, so the vertex is still 0, 0, because I didn't do anything to the inside or outside. I didn't do the plus, you know, it's invisible plus 0 behind. So my vertex is still 0, 0, 0. However, this 1/4, because it's multiplying to the function, what it does, it takes basically every point and multiplies it by 1/4. So if it was an example, if it was sitting at location 4, now it's at a location 1. Every single point gets compressed, and that's actually what it's called. It's the vertical compression, which is opposite of stretch. Stretch is, you know, making something longer. In this case, longer meaning steeper. But otherwise, in this case, it takes every point and compresses it down. So this point right here, which used to be at at 4, now it's at 1. So I'm not gonna go through every single step here, because it's just the hassle of I don't know. I guess an 8. 8's easy enough, because 8 is going to go to 2, right? 8 is going to go to 2. I think you know, like that the y value there is going to get compressed by a factor of 1/4. In other words, divided by 4. Same thing on the positive side. This 8 would be compressed down to at 3 would be compressed to where? To 2. So this would look like this, kind of an open parabola, right? Notice it's wider than this is the parent. In fact, I could, if I were to move this, the ones I was going to transform this originally over here, and then kind of sorry, not compress, but vertical stretch. So this actually would look very narrow in this location. Okay. However, if I'm kind of jumbling a couple of examples all at once, because they were I'm just going from one example to another pretty quickly. So if I have a fraction here, this is a fraction. Could be positive or negative. The negative part, if I was negative, it would be upside down. It would be like this. Like exactly like this blue, or the same. I don't want to say exactly, but it would have that shape, but upside down. That's the negative. That would be the negative exponent. Negative coefficient. So let me clear that one. All right. So if it's a fractional coefficient in front, it leads to a wide parabola. And I'm using the word parabola. I'm using the quadratic to demonstrate all transformations. Even if it was a different function, it would have the same effect. So yeah, don't think that this only applies to parabolas. Any function. So in fact, let's actually do this. So if I were to say a generic function f of x, of y equals f of x, but I'm going to list it a little bit more complicated. It's like that's the parent function, but I'm going to say y equals, let's say, a times f of x, f of, and this is plus d. The only thing I'm not complicated, because right now I definitely don't feel comfortable in the same video complicated by really complicating on the inside part, right? And of course, it depends on the complexity of the function, whether it's a square. If it's a linear function, then it's really easy to complicate it and not be too concerned about it. But the more complicated the original function is, the more complicated your complications are, because that would be a complication on that. Anyway, so let's discuss what these things, or recap what this is. If it's outside the function, This is the inside the function transformation. This is outside. This is vertical shift. Either up or down, depends whether this is positive and negative, of the whole graph. On the inside, this is horizontal shift by C. So in this case, it's a vertical shift by D. So if D is positive, then it goes up. If D is negative, it goes down. In this case, if C is positive, then it's gonna look like X minus, let's say X minus 4. So it's a horizontal shift. Horizontal means in the side direction. But in this case, this is either like this by C, or if this is by negative C. And the negative C would just look like inside here, it's like X plus 5. Well, that's a negative shift because we have a positive number here. So C must be negative 5. Okay, so I'm going to undo that last one so that doesn't. All right, and what about this letter A out front? I'll use do. Well, that is a vertical stretch. Now, technically it's vertical stretch or compression. I'm going to abbreviate it. Compression. If A is a fraction, then it's compressed. Then it's getting flatter. And when you're using the example of quadratic, if it was like, if this is 1/10, then it would be a very, very wide open, very slow rising parabola. As an example, if this is A equals 1/10. On the other hand, if A equals positive 5, then it would be a pretty steep parabola, very steep. And the higher, the greater the number, the steeper it is. And lastly, or a recap, what if this A is a negative number? Well, it's a reflection about the vertex. Actually, it's about so I could move it and reflect it about the vertex. Okay, all right. I think that might be. Okay. No, I actually meant to talk about odd even functions. Oh, it is getting kind of long as the video. So I might want to stop and make a new video of this. I think I will stop. I will do that because this is pretty long as it is. All right. I'll see you in class.